Hi everyone, my name is Yassine Ralim and I'm a principal at Sunstone. For those that don't know us, we are a 10-year-old early-stage technology venture fund based in Copenhagen and Berlin and investing all across Europe at seed and Series A. Over the past couple of years, we found ourselves investing in several AI and machine learning-enabled companies in areas as diverse as marketing, credit scoring, recruitment, fertility tracking, and so on. Most importantly, more and more of our other portfolio companies are starting to adopt these technologies in order to make their products better. What follows is a presentation that we gave to our LPs at our most recent Investor Day. We tried to give them a primer on these technologies, what they are, why we are all talking about them now, and how we at Sunstone are thinking about investing in that space. We thought that we would share it with everyone else, and I hope you enjoy it. Right, so everyone is talking about AI and machine learning. What you see here is an index that represents the number of mentions of artificial intelligence in English-speaking tech media. And the point is that attention to these technologies has really been growing exponentially. And the conversation around these technologies usually centers around that. AI is either going to move mankind to a superior state, or it's going to put us all out of a job before killing us all. And I'm not saying that this is not an interesting debate, but those are more philosophical or societal questions. The first thing we wanted to do is to explain what these technologies are at a high level. So if we start with artificial intelligence, well, what AI is a 61-year-old branch of computer science that uses algorithms and techniques to mimic human intelligence. So there are really two important points in this sentence. The first one is that it's old. And the five gentlemen that you see on the slide are the five founding fathers of AI. In 1956, they gathered at Dartmouth University and theorized the discipline of AI. So they defined the objectives that they set for themselves and for future practitioners, as well as the plan to get there. The second point is this idea of mimicking human intelligence. So what does that really mean? Well, the end goal of AI in 1956, just like today, has always been to build an artificial generalized intelligence, or AGI. For those of you that watch the movie Ex Machina, an AGI is pretty much what Ava is in the movie. It's this fully autonomous robot with IQ and EQ and creativity and moral. And so that's the end goal. So the question becomes, how do we get there? And the answer back then in 1956, and to a large extent still today, is to break down what we define as human intelligence into some discrete components, some of which you see on this slide: logical reasoning, understanding human language, and so on. And then the hope was that, if we worked on each of them separately and then one day put them all back together, then maybe you'd get Ava. Right, so we talked about AI. How about machine learning? Okay, so here you see a simplified taxonomy which should help clarifying things. As we explained, AI is a branch of computer science, like many others. And if you zoom in on AI, you find some sub-branches underneath, and ML is basically one of them. That's because there are 7 different ways to get computers to perform the kind of sophisticated cognitive tasks that humans do, and machine learning is just one of them. So the focus of machine learning at the high level is to give computers the ability to perform those sophisticated cognitive tasks without being explicitly programmed. And I'll explain, what makes it so special later using some examples. Right, so machine learning is one technique, and that's really the point of this slide. It was born in the 1950s, and as of today, this is the favored technique, but it wasn't the case back at the beginning. And then if you try to go one level deeper and you zoom in on machine learning, again, what you find is an array of different techniques. The two most talked about today are deep learning and reinforcement learning, but there are also plenty of others. So the point here is really that there are different approaches to AI. And as a matter of fact, the history of AI is really a history of successive hype cycles about the prospects of some of these techniques. And I won't go over the details here, but the point is that if you study the history of AI, you'll find that it follows a pattern. Every 10 years or so, everyone gets super excited about the prospects of a technique. People think that this is it. This is what will get us closer to the end goal, to AVA on the previous slide. And there's lots of research and funding and interest by the media and everyone. And then people realize that it's not as good as they thought, and they get disappointed. And this is a phase that people have called an AI winter. It happened so many times that they even coined a name for it. And the point here is really that we are very much on the way up of one of these cycles. And everyone wonders if this time is different or if we will inevitably follow the same pattern. All right, but what is it that makes machine learning different? As we just saw, there are several techniques within AI, but machine learning is very interesting because it's kind of different from all the other ones. It's a real paradigm shift. Why? So let's say you want to solve a particular problem, like identifying cats. All traditional AI techniques would program the computers to recognize a cat. They would say, hey, we know how to recognize a cat. A cat is a small animal, it has 4 legs, it has ears, a long tail, fur, and so on. Well, if we know that, let's just write all this logic into a piece of software and then use it to recognize the next cat. So they all basically come from a position where you say you're an expert in a task and you know the logic, and you then use that logic as input to perform the task. Well, machine learning's premise is that it doesn't know the logic of how to recognize a cat. That's actually what it's trying to figure out. In that sense, machine learning algorithms are one level more abstract because they are algorithms that output another algorithms. And it sounds a little bit complicated, but the idea behind it is very simple. You show a lot of pictures of cats and of other things, and then the other thing you tell the computer is which one is a cat. And then you let it come up with the general rule of how to recognize cats, the logic. That's why in machine learning, the logic is inferred from the data. Right, so let's maybe look at this through an example. The game of Go. So Go is this 2,500-year-old board game played a lot in China and in Korea, where two people face each other like checkers or chess. But what's different with Go is that it's a lot more complex than chess. The average turn in chess offers about 35 possible moves, when a Go turn offers 250 possible moves. So it's a lot more complex. If we wanted to get a computer to excel at playing the game of Go, and we asked the tenants of the 3 main branches of AI how they'd go about that, well, you'd get the following answers. The tenants of symbolic AI would say, that's easy, let's just sit down with the world's best Go player, Lee Sedol, and put his knowledge into a computer program. The tenants of mathematical or statistical AI would try to use brute force. So they'd say, let's just simulate all the different possible moves and the associated outcomes at every single step, and then we'll go with the most likely to win. And finally, the tenants of machine learning would say, let's just show millions of examples of games, won and lost, to the program, and let it learn from experience and just figure out the best way to play by itself. Right. So if we try to understand if there's a common denominator to define the type of tasks that machine learning is particularly good at solving, Well, I think that there are really two types of problems where machine learning shines. And the best way to think about that is to look for the type of tasks that other techniques cannot do well. The first one is intuitive tasks that programmers cannot describe, like how to decipher human handwriting or how to teach someone how to ride a bicycle. Those are things that we all do intuitively. And I myself wouldn't be able to put it into words, let alone algorithms. The second set of tasks are tasks that are too complex. They are multidimensional problems where you have way too many variables to consider. You just cannot look at all the different possibilities and compute your way out of it. It's way too complex. Even the most powerful computer wouldn't be able to do that. So the best way to solve these problems is to approximate what looks like a good enough answer based on experience. And this is pretty much what machine learning does. You can see examples of such tasks here. Is this a cancer cell? What should be the price of this house? Is this rocket going to take off? Yes or no? Am I going to like that movie? Yes or no? The important point is that machine learning never says the answer is that. It always says there's a pretty good chance that the answer is that based on past examples. All right, so we talked about AI and machine learning and their relationship, and we explained what made machine learning a different type of AI technique. As we saw earlier, machine learning is very much the technique of the day. And we are in the middle of a new hype cycle around the prospects of this technique to get us closer to the end goal. Why is that? Why the new hype cycle? At the high level, I think it's for two main reasons. The first one is that in a short 5 years, we have made unprecedented progress in solving very difficult problems that defied our best efforts for more than 50 years. Problems like recognizing human speech, recognizing objects in pictures, automatically translating human languages. Those are some of the tasks that the founding fathers of AI were already talking about back then, and then that generations of some of the smartest minds on the planet tried and failed to get close to human level of performance. But we've seen real breakthroughs recently. The second reason is that for the first time in history, AI is leaving the lab. It's finding its way into products that you and I use on a daily basis. It's in our phones, it's in our homes, it's in our cars already if you're driving a Tesla. Right, but why now? If we look at it more granularly, we'll find that there's not a single reason, but really a confluence of 4 key factors that came together and created a perfect storm, which makes this particular AI hype cycle quite special. The first one is that, as we said, AI is 61-year-old. It's not a new field, which means that researchers have been working on these algorithms for a very long time. And that includes neural networks, which are behind a lot of the breakthroughs that we mentioned. They have had the time to mature in the lab. The second reason, and that one is pretty new, is that we now have a lot of data. We live in the information age, and the amount of data that we produce has been increasing exponentially. And this is really key since data is the chewing material for those machine learning models, in particular deep learning models that need a lot of data to generalize well. So this has been really important. Right, so we had mature algorithms and lots of data, but this is not very useful if you don't have enough computing power to train the models on that new data, which is the third key factor here. We've seen a real step change in our computing resources. This is partly because of Moore's law, but mostly because since 2012, researchers and AI practitioners started to use GPU chips instead of CPU to train their deep learning models. At the high level, the reason is that deep learning involves a lot of linear algebra, which means multiplying matrices, which means making a lot of calculations at the same time. And that's something that GPUs are great at. To give you an order of magnitude, a model that takes a couple of minutes to train today would typically have taken around 24 hours to train 10 years ago, and something like 400,000 years 20 years ago. So this third point has really been a game changer. Right, so mature algorithms, data, computing power. And the last point is that access to these technologies has really been democratized because a lot of the large tech companies, Facebook, Google, etc., all released open source libraries and frameworks for free for anyone to use. These are essentially foundational AI components. They are resources that a developer needs to conduct experiments and build and deploy AI technology. So access to these technologies has really been democratized. You don't need to be working at a university lab to play with these technologies anymore. And that's also why we're seeing more and more AI products reach us today. Right. So where are we now? What can AI and in particular machine learning and deep learning do? At the high level, what we've seen recently is AI systems that reached equal to above human performance at some narrow tasks. And we'll look at that through one example that I think is a good illustration of where we are. Right, so this is something that happened 3 months ago. A team of Google researchers built a machine learning model as good at diagnosing diabetic retinopathy than trained ophthalmologists. Diabetic retinopathy is a very serious medical condition. It's the fastest growing cause of blindness in the world, and it's a complication of diabetes. The picture in the top left corner shows what diabetic retinopathy feels like. The patient fields of view basically gets progressively covered by those black spots up until the point where the patient becomes completely blind. And the key to preventing irreversible blindness is to detect it early, which you can do by doing regular screenings. Now, that's something that's practically impossible in many parts of the world where there's a shortage of doctors, and it's also quite expensive. The way human doctors diagnose it is by taking a picture of the back of the eye through the retina and then looking for small spots on the image, and they do that manually. So the question that Google asked was, can we teach a machine learning model to diagnose diabetic retinopathy just as well as trained ophthalmologists and using the exact same methodology? So by looking for those patterns in the pictures. So they first gathered a training set of 130,000 of these images, some of them with, some of them without diabetic retinopathy. And then they got 7 ophthalmologists to annotate each picture. So that's a massive endeavor, and it took them a lot of time and money to build that training set. Then they fed the computer these labeled images and let it try to generalize a rule to separate bad and good cases. And once that model had been trained, we can see it in the short video here, they used the logic that was inferred to assess new pictures that the model had not seen before. So you feed a picture to the computer and it says, yes, this is a case of diabetic retinopathy, or no, this isn't. So it's a very good study because this is exactly how ophthalmologists perform these tasks. So you get to really compare the level of performance of the AI and of the trained human doctor, which is what they did. So what you can see on the right are the results of this study. And here, a perfect performance on this chart means a dot at the top left corner. So the dots that you see in color represent the performance of the human doctors, and the black dots, the performance of Google's model. And the point is that Google's system performed almost on par with human experts. So this is an example of a narrow task where AI has almost reached human performance level. And you could say, well, what's the big deal, right? Humans are still slightly better at this. And that's absolutely true, except that it probably costs under a cent per patient to run the model, which is a lot less than a consultation with an ophthalmologist would cost. And there are many places on Earth where people don't have access to ophthalmologists and where this could make a real difference, like India, where this model will soon be deployed into production. All right, so we've just seen that AI and machine learning systems were starting. All right, so we've just seen that AI and machine learning systems were starting to reach equal to above human performance at some narrow tasks. And we've looked at that through one example. But what is it that they still cannot do well? So the first thing is those deep learning models. No, let's do it again. Take 4. So the first thing is that those machine learning models still need a lot of training data to reach state-of-the-art performance. And we've just seen an example previously of a machine learning and deep learning model in particular that was able to do amazing things with lots of data. Remember that Google got 7 trained ophthalmologists to each annotate 130,000 eye pictures, which is a tremendous effort. But the problem is that you don't always have huge data sets on everything. Something like that is the exception rather than the rule. So this is one of the main problems that we haven't solved yet. How do you get neural networks to generalize well from small amounts of data without seeing patterns that are not there, which is called overfitting in machine learning? And this is one of the major areas of research in the field currently. Doesn't mean that we're not going to get there. As a matter of fact, super smart people are working on techniques that would allow those networks to reach the same level of performance from very small data sets. But this is an area where we're back to the lab. The second thing that those models cannot do well yet is learning to learn. Right now, those models that reach state-of-the-art performance at a given task, like the one we've seen before, are essentially mimicking training data. This is called supervised learning. And if we stick with the Google example, that model was fed with lots of pictures that had been previously annotated by ophthalmologists as with or without diabetic retinopathy. This is a fully supervised case. You explicitly tell the computer what is a good and what is a bad outcome, and you let it generalize a rule based on what it has seen before. Now, the overwhelming majority of the algorithms that we have in our lives today fall in that category. But that's not really how children learn. Unsupervised learning is very much still in the column or challenges. In the previous example, the unsupervised version would be to feed the computer with raw pictures without telling it that this is a good or a bad picture and letting it figure it out by finding structure in the data, perhaps by asking a series of questions. Again, it's a super important area within machine learning because when we get there, we will be able to take advantage of a lot more data out there in the world that is just not labeled yet. But once again, here we're back to the lab. And finally, the third and last thing is that machine learning models are becoming excellent at performing narrow tasks like diagnosing diabetic retinopathy. And that's absolutely great in itself, but we're still very far from generalized human intelligence. We're still very far from AVA that we saw on one of the first slides. And it's not the first time that we significantly underestimate the length of the path ahead. What you see here on this slide is a New York Times article from 1958, 2 years after the birth of AI as a discipline. And back then, the US Navy had built a computer program that had learned how to differentiate between right and left, which is a very narrow task. And what you already saw back then was that hopes were getting inflated. The researchers that had built this program thought that it would soon be able to walk and talk and see and write, reproduce itself, and even be conscious of its own existence. Obviously, that didn't happen. And there's a bit of a parallel with what we're seeing today, right? So we're becoming good at a lot more of these narrow tasks. Some of them are super important and valuable, but that doesn't mean that we are getting anywhere close to the end goal. All right, so in this final section, we wanted to explain how we at Sunstone have been thinking about that space from an investment perspective. Right, so first, we are firmly of the view that AI and machine learning are the next major horizontal enabling technology, just like cloud, mobile, or social before them. We talk about it as a theme, as an investment area today, just like back then we talked about cloud and mobile as a theme. But soon we won't, as what they are is really a horizontal technology. We do think that they will transform every industry and make every product better. So even if we're pretty far from AGI, it's still a big thing. Which is why a lot of money went into companies focusing on these enabling technologies. AI-enabled companies attracted 17 times more funding in 2016 than in 2010, and we are on our way to see more than $4 billion invested in these companies globally this year. So it's a great opportunity, but investing in these companies is also not without challenges. The first challenge in our mind is really timing. We are at a point in the hype cycle where the signal-to-noise ratio is becoming increasingly low. And what you see here is the 2016 Gartner hype cycle with machine learning and deep learning right at the peak. Now, the good news is that the plateau of productivity isn't far away in numbers of years. This is when AI and machine learning will stop to be seen as a theme and just become an integral part of every product and industry. But it seems quite likely that we will see a phase of de-hyping before that. This is also our empirical observation on the ground. It's pretty clear today that there's a lot of money chasing companies because they're using these technologies, which is something that we consciously refrain from doing. And as an illustration of that, this is a funny anecdote that happened at NIPS 2016 in Barcelona, the main AI conference where the leading AI practitioners gather to discuss advances in the field. A group of AI observers created a completely fake company, Rocket AI, and announced its launch during the conference. They put up a website, they released a paper, they even held a small conference where they talked about their groundbreaking approach, temporarily recurrent optimal learning, which it turns out is just a combination of buzzwords they put together to spell out troll. And in a few hours, it was all over the web. Some people attending the conference called it the biggest breakthrough in AI history. 300 people wanted to attend their party. 50 people emailed their resume. 5 VCs contacted them about investing. So this was all fake and just illustrates the previous point around timing and where we are in the hype cycle. Now, besides timing, the second big challenge about investing in that space is that startups are competing with a very different type of incumbent. In many cases, they are competing or likely to end up competing with today's technology giants. These companies all got the memo that AI was a big thing. They are betting their future on that. They have more money than startups can dream of. They have more data than most startups in many domains. They can hire all the leading AI researchers. Basically, they get the game, they are aggressive, they don't want to be disrupted, and can outcompete startups by releasing products for free because they're subsidizing them elsewhere, or if they really feel threatened and want to get their hands on the talent, they'll try to buy startups early, which in 95% of cases doesn't yield the type of outcomes that venture funds need to make their model work. All right, so what is our investment thesis in the face of these risks and opportunities? As much as we always try to keep an open mind, there are a few guidelines that we set for ourselves. So this one sounds very obvious, but it's actually very important. Problems always come first. We do not invest in companies because they're using a particular technology. We invest in companies solving important problems. And there are a lot of problems that these technologies can solve, whether that's automating repetitive tasks previously done by humans at a marginal cost close to zero and with similar or even better performance, or augmenting humans by allowing them to be better at what they currently do. But the point is that those problems have to be the starting point, not the other way around, and those problems have to be important. The second thing is that, yes, there are very aggressive incumbents looking at how to use these technologies to perform a lot of different tasks, but they're not going to go after every problem in the world. This is especially true of vertical niches. The tech giants are mostly working on the broad problems in AI, image, video, speech recognition, NLP, AGI, mobility to a certain extent. And we think it's quite hard to build a startup going after those broad horizontal problems that has a chance of becoming a large standalone company. However, we think that startups can really thrive in vertical niches, and we have focused all of our investments there. The third thing is that we believe that data is not the only, but a major source of defensibility in that space. Just like anywhere else, the combination of the best execution and the best product ends up winning. But with machine learning enabled companies, product and data are kind of tied at the hip. The main driver of what makes a machine learning enabled product good comes back to the accuracy of the underlying algorithms at performing a given task. And that largely comes back to the quantity, the quality, and the uniqueness of the data on which those algorithms have been trained. This is what people describe as data network effects. So we think it is very important to have access to a proprietary dataset. It's a real differentiator. And there is not one single way to do that. Our portfolio companies are all thinking about this point differently, but it's a key factor that we always assess when we invest in the space. And finally, we prefer when companies are getting paid to collect this proprietary dataset. And here, not all investors agree. As a matter of fact, this is a common dilemma for these companies. Do you get to work with a few customers to make revenues, or do you postpone revenues to get as much data as possible, sometimes pay for it even to build defensibility around your business? It's a little bit reminiscent of social. Do you go for number of users, or do you try to monetize them early on? And here we really like it when companies get paid to collect data. We think that it adds longevity, and as always with startups, there are things that never change. Just like gravity, startups die when they run out of money. They need to be able to raise successive funding rounds, they need to reach milestones. So we really favor companies starting with an easy enough industry problem that they can solve right now, getting paid for it, to then get more data and build better products in the process of doing that. Right, so this is it for today. I hope you enjoyed it. If you have comments or questions, by all means, get in touch. If you want to learn more about why we invested in specific companies, look for the blog posts we have on some of them. And if you're building a company in the space, we'd love to hear from you.